The night of August 19th, 1944. South China Sea, approximately 200 miles southeast of Hong Kong. A lone B-24 Liberator designated Nitemare descends through absolute darkness toward the surface of the ocean. Inside the nose compartment, 23-year-old bombardier Lieutenant John Shytle stares not through the famous Norden bombsight's optical telescope, but into a small green radar scope mounted directly above it. The scope shows a bright return echo. A Japanese heavy cruiser, 5,000 tons of armored steel, moving at 18 knots through water, the Americans aren't supposed to be able to see. Shytle's hands move across unfamiliar controls, not the mechanical dials and knobs of the standard Norden, but electronic switches that feed radar returns directly into the bombsight's analog computer. The aircraft drops to 300 feet above the wavetops. At this altitude, in total darkness, without visual contact with the target, what Shytle is attempting should be impossible. The Norden bombsight was designed for high-altitude precision bombing in clear daylight. Using it at 300 feet, at night, guided only by radar, violates every principle the device was built on. The crosshairs on Shytle's scope center on the target blip. The bomber's autopilot. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Linked to this hybrid radar optical system makes minute corrections to heading. The radar computer calculates range, speed, bearing. At exactly 02:17 hours, the intervalometer triggers automatically. 6 500-pound bombs release in precise sequence, each spaced 75 feet apart. Shytle doesn't see the bombs hit. Nobody does. But the radar scope tells the story. The bright return echo fragments, then fades, then disappears entirely. 5,000 tons of Imperial Japanese Navy warship has just been sunk by a weapon system so secret that fewer than 200 people in the entire United States military know it exists. This is LAB, low altitude, bombardment, and the story of how it came to exist begins not in 1944, but 3 years earlier, in the wreckage of American bombing doctrine. December 7th, 1941. Pearl Harbor burns. The Japanese surprise attack doesn't just destroy battleships and aircraft, it destroys an assumption. American military planners had spent the 1930s building an entire strategic doctrine around high-altitude daylight precision bombing. The theory was elegant. Heavy bombers like the B-17 and B-24, flying at 20,000 feet or higher, would use the Norden bombsight to hit specific industrial targets with surgical accuracy. The bombers would be too high for effective anti-aircraft fire. Their defensive armament would ward off fighter attacks, and the Norden's gyroscopic stabilization system would deliver accuracy measured in feet, not miles. Pearl Harbor revealed how little of this doctrine had been tested against actual combat conditions. Within weeks, American bombers were flying missions in the Pacific. The results were catastrophic. B-17 seconds attacking Japanese shipping in the Philippines achieved almost no hits. Bombardiers trained to operate at 20,000 feet suddenly found themselves flying at 12,000, 10,000, sometimes 8,000 feet, trying to get below cloud cover that obscured their targets. The Norden bombsight, calibrated for high-altitude bombing, produced terrible accuracy at these lower altitudes. Even worse, the optical system required visual contact with the target. If clouds, darkness, or smoke obscured the target, the bombardier was essentially blind. By March 1942, the Navy's Bureau of Aeronautics was receiving disturbing reports from the Pacific. Anti-shipping operations were failing. Bombers would locate Japanese convoys, line up perfect attack runs, and watch their bombs miss by hundreds of feet. The problem wasn't the bombardiers or the aircraft. The problem was the fundamental limitation of optical bombing. You can't hit what you can't see. And in the Pacific theater, between weather, smoke, and the Japanese preference for nighttime resupply runs, bombardiers often couldn't see anything. This is where the story should pivot to some genius inventor working alone in a basement. That's not what happened. What happened was messier, more bureaucratic, and ultimately more interesting. The solution to optical bombing's limitations already existed. It just wasn't being used correctly. Radar had been around since the late 1930s. By 1942, American bombers were already being fitted with search radar sets like the SCR-717, which could detect ships and land masses from 50 to 70 miles away. The radar operator, stationed in the waist of the aircraft, would scan for targets and call out their position to the pilot. But there was a massive disconnect. The radar operator could see targets on his scope. The bombardier, staring through the Norden's optical telescope, could not. The two systems operated independently. The radar found targets, the Norden aimed at targets. But they couldn't talk to each other. The first attempts to combine radar and optical bombing happened in Europe, not the Pacific. By late 1942, the 8th Air Force was discovering that European weather made high-altitude precision bombing nearly impossible. Germany and occupied Europe spent half the year under cloud cover. Bombardiers would fly 6-hour missions, arrive over the target, and see nothing but clouds. Some missions resorted to radar-assisted area bombing, where the radar operator would identify a general location, like a city, and the bombardier would release bombs based on timing and dead reckoning. This wasn't precision. This was throwing explosives at a map grid and hoping they landed near something important. The British had developed H-2S radar for this purpose. It was a ground mapping system that showed terrain features and cities as bright returns on a cathode ray scope. The Americans adopted it and called it H-2X, or Mickey. By early 1943, some American bombers were equipped with H-2X, and it helped with navigation and target identification. But it still didn't solve the accuracy problem. You could see a city on radar. You couldn't bomb a specific factory building within that city, not with any precision. The radar image was too blurry. A building looked like a bright blob. 100 buildings looked like one larger bright blob. Some engineers proposed feeding radar returns directly into the Norden bombsight's computer. If the radar could measure range and bearing to a target, and the Norden could calculate bomb trajectories, why not connect them? The idea made theoretical sense. The practical execution was a nightmare. The Norden was an analog mechanical computer built with precision gears, cams, and gyroscopes. It expected inputs in a very specific format: altitude, airspeed, wind correction, trail angle. It wasn't designed to accept electronic signals from a radar scope. Modifying it would require completely redesigning its input mechanisms. Moreover, the Norden was classified at the highest secrecy level. Bombardiers swore oaths to destroy the device before letting it fall into enemy hands. Armed guards escorted it to and from aircraft. The idea of letting radar technicians and electronics engineers tinker with America's most secret weapon system made military planners extremely nervous. Carl Norden himself, still alive and still obsessively protective of his creation, actively opposed any modifications that he hadn't personally approved. But by mid-1943, the strategic situation had shifted in ways that made these concerns secondary. American forces were advancing across the Pacific. Islands were being taken, airfields constructed. The problem was no longer finding targets. The problem was hitting them at night. The Japanese had learned, painfully, that daylight operations near American-controlled airspace meant getting intercepted by fighters. So they ran supply convoys at night. They moved troops at night. They conducted naval operations under cover of darkness. American patrol aircraft with search radar could locate these night convoys. But they couldn't attack them effectively. Torpedoes required visual contact for the final attack run. Bombs dropped from altitude at night hit nothing. The Japanese were operating with near impunity in darkness. The Navy's solution was to give the problem to a small group of engineers who didn't particularly care about doctrine or tradition. They cared about making things work. In late 1943, a team at the Naval Research Laboratory in Washington began working on what they called the Low-Altitude Bombardment System. The name was deliberate. This wasn't an attempt to fix high-altitude bombing. This was a completely different approach. The insight was simple but revolutionary. If you're flying at low altitude, below 1,000 feet, you don't need the Norden's complex gyroscopic stabilization system. At low altitude, atmospheric turbulence is minimal. The aircraft is relatively stable. What you need is accurate range and bearing information, which radar provides better than optics. The team proposed stripping out the Norden's optical telescope and replacing it with a radar scope. The bombardier would aim using radar returns instead of visual sighting. The Norden's mechanical computer would calculate trajectories based on radar-derived data instead of visual tracking. This required solving several technical problems. First, radar returns are fuzzy. A ship on a radar scope appears as a bright blob, maybe 30 or 40 pixels across. How do you aim precisely at a fuzzy blob? The answer was to add electronic crosshairs to the radar scope. The bombardier would manually center these crosshairs on the target blip. As long as the crosshairs stayed centered, the radar was providing accurate bearing information. Range came from the radar's built-in distance measurement. With bearing and range, the Norden's computer could calculate the bomb release point. Second problem. The Norden expected continuous tracking. The bombardier was supposed to keep the optical crosshairs on the target throughout the entire bomb run, allowing the mechanical computer to calculate ground speed, drift rate, and trail angle. But a radar scope doesn't track smoothly. The radar antenna rotates, sweeping across the target. Each sweep produces one radar return. The target blinks in and out of existence on the scope, appearing once per antenna rotation. The team solved this by increasing the radar's scan rate and adding electronic circuits that held the target position between scans, creating the illusion of continuous tracking. Third problem. The Norden's autopilot interface. The standard Norden system could control the aircraft during the bomb run, making small heading corrections to keep the bomber on the correct trajectory. This was essential for accuracy. But the autopilot expected inputs from the optical tracking system. It needed to know which direction the target was moving in the bombardier's field of view. The team had to build electronic converters that translated radar-bearing data into signals the autopilot could understand. This required understanding both the Norden's mechanical computer logic and radio frequency engineering. The number of people in America who understood both disciplines in 1943 could probably fit in a single room. By January 1944, the team had a working prototype. They called it the RC-17 LAB sight. It consisted of three main components. First, the SCR-717B search radar, mounted in the waist of the aircraft, with its antenna under a plexiglass dome. This radar had a range of 200 miles at 3,000 feet altitude. Second, the APQ-5, bombing computer, an electronic unit that interfaced between the radar and the Norden bombsight. Third, the modified Norden itself, with a 5-inch radar scope mounted directly above the optical telescope. The bombardier could switch between optical and radar modes, though in practice, once you started a radar bomb run, you stayed in radar mode. The system was tested at the Naval Proving Ground at Dahlgren, Virginia. The tests used target rafts in the Chesapeake Bay, the same location where Carl Norden had tested his original bombsight 15 years earlier. Except now the testing happened at night. The bomber, a modified B-24D, would take off after sunset, fly out over the bay at 300 feet altitude, locate the target raft using the search radar, transition to LAB mode, and release practice bombs. The goal was to place bombs within 100 feet of the target from an altitude of 300 to 500 feet. The initial results were mixed. On some runs, the system worked perfectly, placing bombs within 50 feet of the raft. On other runs, bombs missed by 300 feet or more. The problem wasn't the technology, the problem was the bombardiers. They'd been trained for years to use optical sighting. Looking through the Norden's telescope had become instinctive. Now they were being asked to ignore that instinct and trust a glowing green dot on a cathode ray screen. Every instinct told them to look out the nose at the target. But at 300 feet altitude, at night, there was nothing to see except darkness. The solution was to literally blind them. During training flights, the bombardiers sat in nose compartments with blackout curtains covering all the windows. They couldn't see outside even if they wanted to. They had to trust the radar, trust the computer, trust the system. This psychological adjustment took time. Some bombardiers adapted quickly. Others never fully trusted radar bombing. The ones who adapted became, effectively, a new type of warfare specialist. Not quite pilots, not quite bombardiers in the traditional sense. They were radar targeting officers, reading electronic displays and trusting mathematics instead of eyesight. By March 1944, the system was ready for operational deployment. The Army Air Force activated the 1st Sea Search Attack Group at Langley Field, Virginia. This was the cover designation. Nobody was supposed to know what Sea Search Attack actually meant. The group consisted of 3 squadrons, each with 10 modified B-24 bombers. These weren't standard B-24 seconds. They were designated SB-24, with the S standing for Special. Each aircraft had the LAB system installed, plus additional fuel tanks for extended range, specialized navigation equipment, and a full suite of electronic countermeasures. The crews were hand-picked. Most came from anti-submarine patrol units, men who were already comfortable with low-altitude flying and radar operation. They underwent 6 weeks of intensive training at Langley. The entire training program was classified. Crew members weren't allowed to discuss their training even with other aircrew on the base. If asked, they were instructed to say they were training for long-range maritime patrol, which was technically true but deliberately vague. 2 squadrons were sent to the Pacific Theater. The 868th Bombardment Squadron went to the South Pacific, initially stationed at Guadalcanal, operating against Japanese shipping in the Solomon Islands and Bismarck Archipelago. The 63rd Bombardment Squadron went to China, joining the 14th Air Force under General Claire Chennault. Both squadrons arrived in theatre in June 1944. Both began night operations immediately. Neither had any real idea whether the LAB system would work in combat. The first combat test came on the night of June 23, 1944. 3 B-24 seconds from the 868th Squadron, operating from Munda Field in the Solomon Islands, were tasked with interdicting a Japanese resupply convoy heading for Bougainville. Naval intelligence had reported 8 transports and 4 destroyers, carrying nearly 3,000 troops and supplies. The convoy was scheduled to transit through St. George's Channel, a narrow passage between New Britain and New Ireland, arriving at Bougainville after midnight. Perfect conditions for a night attack. The SB-24 seconds took off at 2200 hours. Each aircraft carried 6 500-pound bombs configured for ship attack, with nose and tail fuses set for instant detonation. The flight profile was simple. Climb to 3,000 feet for transit. Use the SCR-717 search radar to locate the convoy. Descend to 400 feet. Switch to LAB mode. Attack individually at 30-minute intervals to maximize confusion and minimize the chance of Japanese fighters vectoring onto multiple aircraft. The lead aircraft, call sign Coral Princess, piloted by Captain Franklin Reynolds, picked up radar contacts at 01:15 hours, range 60 miles. The radar operator identified 11 distinct returns, consistent with the intelligence estimate. Reynolds selected the largest return, assessed as a cargo vessel approximately 400 feet long. He began his descent, dropping from 3,000 feet to 400 feet over the course of 8 minutes, watching his airspeed carefully. The LAB system required a specific attack geometry. Aircraft altitude between 300 and 500 feet, airspeed between 130 and 140 knots, attack angle 90 degrees to target course. At 400 feet and 135 knots, Reynolds called for LAB activation. Lieutenant Shytle, the bombardier, confirmed radar mode. His scope showed the target clearly. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. A bright return approximately 4 miles ahead. He centered the electronic crosshairs on the brightest part of the return, clutched in the autopilot, and watched the Norden's computer begin calculating the solution. The APQ-5 bombing computer was receiving range and bearing updates from the radar 10 times per second. It was feeding corrections to the Norden's mechanical calculator, which was solving ballistic equations using brass cams and gears, spinning at thousands of revolutions per minute. The attack geometry was different from high-altitude bombing. At 20,000 feet, bombs took 40 seconds to fall, traveling forward nearly 2 miles during that time. The bombardier released when the target was still miles away, trusting mathematics to arc the bombs onto the target. At 400 feet, bombs took less than 5 seconds to fall. The bomber flew almost directly over the target before releasing. It was more like strafing than bombing. You approached, you released, you were past the target before the bombs even hit. At 01:23 hours, the APQ-5's computer signaled optimal release point. The intervalometer triggered automatically. 6 bombs, released in sequence, spaced 75 feet apart. The bomber's airspeed and the bomb spacing were calculated to create a stick pattern that would bracket a 400-foot target. Reynolds immediately initiated a hard climbing turn to port, standard evasive procedure. The bombs took 4.7 seconds to reach the water. From Reynolds's perspective, he saw nothing. No visual confirmation of hits, no explosions visible in the darkness. But the radar operator reported something extraordinary. The target return was fragmenting. Where there had been one large, bright return, there were now several smaller returns spreading apart. Then, over the next minute, those returns began to fade. One by one, they disappeared from the scope. The ship was sinking. Reynolds radioed the other 2 SB-24 seconds, providing target coordinates and confirmation of the LAB system's effectiveness. The second aircraft, Uncle's Fury, attacked 30 minutes later but achieved no hits. Anti-aircraft fire had intensified considerably. The Japanese convoy knew they were being attacked, even if they couldn't see their attackers. Tracers arced into the darkness at random elevations, creating a wall of fire more psychological than effective. But psychological effects matter. The pilot of Uncle's Fury had to maneuver during the bomb run, which degraded the LAB solution. The bombardier released manually, early, and all 6 bombs missed. The third aircraft, Devil's Delight, approached from a different angle, exploiting the confusion. This pilot held steady despite flak, trusting the LAB system to get them through before the Japanese gunners found their range. The attack succeeded. 2 direct hits on a transport, plus 4 near misses that likely caused flooding. The radar return showed progressive fragmentation, consistent with a vessel breaking apart. By dawn on June 24th, naval reconnaissance aircraft photographed the area. They found oil slicks and debris fields consistent with 3 sunk vessels. The convoy had been forced to disperse and alter course, delaying the Bougainville resupply by 48 hours. For 3 aircraft, 6 tons of bombs, and 0 American casualties, this was an extraordinarily successful outcome. More importantly, it proved the LAB system worked. Not in test conditions at Chesapeake Bay, but in actual combat against a defended target in hostile waters. The 868th Squadron flew 73 combat missions between June and December 1944. They operated almost exclusively at night, attacking Japanese shipping throughout the Southwest Pacific. Their target list was diverse: cargo vessels, tankers, troop transports, cruisers, destroyers, even submarines caught on the surface at night. The LAB system proved remarkably adaptable. Ship targets were ideal because they produced strong radar returns against the flat water background. But the system also worked against land targets like fuel depots, ammunition dumps, bridges, anything that produced a distinctive radar signature. The squadron's combat record is documented in classified after-action reports that weren't declassified until the 1980s. By December 1944, the 868th had sunk or damaged 109 vessels, totaling 62,000 tons. That's roughly equivalent to the entire Japanese merchant fleet lost during the Battle of Guadalcanal, except this destruction was accomplished by 10 aircraft operating independently, mostly at night, with minimal support infrastructure. One squadron accomplished what would have required dozens of conventional bomber squadrons operating in daylight. The cost was significant but sustainable. The 868th lost 4 aircraft during this period. 2 were shot down by anti-aircraft fire. 1 was lost to mechanical failure. 1 simply disappeared, cause unknown, presumed crashed into the ocean at night with no survivors. That's a loss rate of roughly 6% per 100 sorties, which sounds high until you compare it to daylight strategic bombing, where 8th Air Force bomber groups were sustaining 10 to 15% losses per mission during the same period. In China, the 63rd Squadron's experience was different but equally valuable. They operated against Japanese coastal shipping in the South China Sea, targeting convoys running between Japanese-occupied ports in China and Southeast Asia. These were critical supply routes. The Japanese garrison in China depended on supplies shipped from Formosa, Indochina, and the Dutch East Indies. Interdict those supply lines, and the Japanese army in China would slowly starve for fuel, ammunition, and replacement parts. The 63rd's most notable mission occurred on the night of August 19th, 1944. This is where we began this story. Lieutenant Colonel James Hobson, squadron commander, led a single SB-24, the Nitemare, on what should have been a routine sea search mission. Instead, his radar operator detected a single large return, approximately 150 miles south of Hong Kong. The return was moving at 18 knots, consistent with a warship rather than a cargo vessel. Hobson closed to investigate. The target was the Italian liner Conte Verde, a pre-war passenger ship that had been scuttled by its crew in Shanghai harbour when Italy surrendered in 1943. The Japanese had refloated it, repaired it, and converted it into a troop transport. On this particular night, it was being towed from Shanghai toward Japan for further repairs, escorted by 2 destroyers and 3 submarine chasers. Intelligence had not reported this movement. Hobson stumbled onto it purely by chance. The LAB attack profile was textbook: descent to 300 feet, attack run at 130 knots, perpendicular to target course. The Nitemare attacked from the southwest, approaching with the moon behind them, making visual detection nearly impossible. Lieutenant Shytle centered his radar crosshairs on the largest return, the transport itself, ignoring the escorts. At 02:17 hours, 6 bombs released. The first 2 bombs were near misses, detonating in the water 15 feet from the hull. The hydrostatic shock was sufficient to rupture hull plates below the waterline. The 3rd and 4th bombs were direct hits, penetrating the main deck before detonating inside the superstructure. The 5th and 6th bombs hit near the stern, one of them detonating directly above the engine room. The transport's power died immediately. It began listing to starboard, taking on water through the ruptured hull. Hobson made one more pass, confirming the damage with radar and visual observation. The ship was clearly sinking. He radioed his base with the target's coordinates and a request for follow-up strikes, then climbed to altitude and returned to Kunming. By dawn, Navy patrol aircraft confirmed the transport was gone, sunk in deep water, with no survivors. The escorts had been unable to tow it or provide effective damage control. This single attack had consequences far beyond one sunk ship. The Conte Verde had been carrying machine tools, precision instruments, and electronics from Shanghai's factories to Japan's war industries. These weren't replaceable items. They represented months of production capacity. Their loss directly impacted Japan's ability to manufacture radar sets, fire control systems, and other electronics. But perhaps more importantly, the attack demonstrated that nowhere in Japanese-controlled waters was safe at night. If a lone American bomber could find and sink a ship in the middle of the South China Sea in total darkness, no convoy was secure. The psychological impact on Japanese naval operations was substantial. By late 1944, Japanese convoys were increasingly reluctant to sail at night without extensive air cover, which Japan could no longer provide. This forced them into daylight operations, where American submarines and carrier aircraft had free rein. The LAB-equipped B-24 seconds created a dilemma with no good solution. Sail at night and risk LAB attacks. Sail in daylight and risk everything else. But the LAB system wasn't perfect. It had significant limitations that prevented it from replacing conventional bombing. First, it only worked at low altitude, below 1,000 feet, ideally below 500 feet. At those altitudes, aircraft were vulnerable to small arms fire, light anti-aircraft guns, even disciplined rifle fire from ground troops. The Japanese learned to defend convoy routes with small patrol boats equipped with automatic weapons. These boats couldn't hit a bomber at 300 feet, but they could force the bomber to maneuver, which degraded LAB accuracy. Second, the radar returns were only as good as the target. Ships produced excellent returns. Large buildings, fuel tanks, and bridges produced decent returns. Jungle, empty ocean, and camouflaged installations produced nothing useful. The system couldn't bomb what it couldn't see on radar. This made LAB unsuitable for many tactical targets. Third, the training requirements were intensive. Converting a conventional bombardier to LAB operation took 6 weeks of specialized instruction. There weren't enough trained LAB bombardiers to equip more than a few squadrons. The system required personnel who understood radar operation, electronics, and bombing calculation. That's a rare skill combination. Fourth, the equipment was temperamental. The APQ-5 bombing computer used vacuum tubes, which failed frequently in the humid tropical environment of the Pacific. The SCR-717 radar used a rotating antenna driven by an electric motor. Sand, salt spray, and jungle humidity destroyed the bearings. Each SB-24 required dedicated radar maintenance technicians who understood both the radar and the bombing computer. These specialists were in critically short supply. Despite these limitations, LAB represented a fundamental evolution in bombing technology. Before LAB, precision bombing required visual contact with the target. After LAB, precision bombing required only a radar return. That distinction becomes crucial when you consider post-war developments. The LAB system's architecture, feeding radar returns into an analog computer that calculated bomb trajectories, became the template for every precision guidance system developed afterward. The lineage is direct and traceable. In 1948, the Air Force began developing the AN/APQ-7 Eagle, an advanced ground mapping radar designed for the B-29. The Eagle used the same basic principle as LAB, translate radar returns into bombing solutions. In the 1950s, this evolved into the AN, APQ-24, and APQ-56 systems, which equipped B-47 and B-52 strategic bombers. These systems could bomb through clouds, at night, with accuracy measured in hundreds of feet rather than miles. The technology had miniaturized enough to fit into tactical fighters. The F-4 Phantom's AN, APQ-120 radar included ground mapping modes derived directly from LAB principles. Laser-guided bombs in Vietnam used similar logic. Convert sensor data into guidance commands that bring the weapon to target. The sensor changed from radar to laser, but the computer architecture remained the same. Modern precision-guided munitions continue this lineage. GPS-guided JDAMs use satellite signals instead of radar, but the computer solving the trajectory problem is still, fundamentally, doing what the APQ-5 did in 1944. Measuring target location, calculating weapon trajectory, compensating for wind and altitude, determining release point. The hardware has changed from vacuum tubes to integrated circuits to microprocessors. The physics hasn't changed at all. Carl Norden died in 1965. He never publicly acknowledged the LAB system, probably because it represented everything his bombsight wasn't supposed to be. The Norden was designed for high-altitude daylight operations with optical sighting. LAB inverted those priorities: low altitude, darkness, radar, but the irony is that LAB proved the validity of Norden's core insight. Precision bombing requires automatic computation of ballistic trajectories. The human eye can't calculate fast enough. You need a machine. Norden built that machine for optical inputs. The LAB team adapted it for electronic inputs. Same principle, different sensors. The men who flew LAB missions didn't think of themselves as pioneers or technology demonstrators. They thought of themselves as bomber crews doing a dangerous job with imperfect tools in hostile conditions. Lieutenant John Shytle, the bombardier who sank the Conte Verde, survived the war and returned to his family's farm in Kansas. He rarely discussed his service. When asked about the LAB system, he described it as bombing by television, which, in 1944, was the only reference point most people had for watching images on an electronic screen. Captain Franklin Reynolds, who flew that first successful LAB mission in June 1944, continued night operations until January 1945, when his aircraft was shot down by anti-aircraft fire over Rabaul. He survived the crash, spent 3 months evading Japanese patrols, and was eventually recovered by Australian coast watchers. After the war, he became a test pilot for Boeing, where he worked on radar bombing systems for the B-47 and B-52. He understood, better than most, that LAB wasn't a finished product. It was a proof of concept. The hardware was crude, the accuracy inconsistent, the operational limitations significant. But it demonstrated that radar-guided precision bombing was possible. The strategic impact of LAB is difficult to quantify. The 2 squadrons equipped with the system flew fewer than 500 combat missions and sunk approximately 220 ships. That's a fraction of the total Japanese merchant fleet lost during the war. But the missions had disproportionate effects. Every ship sunk at night was one fewer convoy attempting the journey. Every successful attack pushed Japanese naval operations further toward daylight, where American submarines and carrier aircraft had overwhelming advantages. More importantly, LAB forced the Japanese to divert resources to night defenses that couldn't be effectively deployed. You can't defend against an attacker you can't see. The Japanese installed searchlights and listening posts along convoy routes. They deployed night fighters, which were expensive to operate and largely ineffective against low-altitude bombers. They assigned escort vessels to convoys that would have been more useful elsewhere. All of these responses consumed resources and provided minimal security. The LAB bombers continued to sink ships throughout 1944 and into 1945. By March 1945, Japanese coastal shipping in the Western Pacific had effectively ceased. Not because LAB had sunk every ship, but because the combination of submarines, carrier aircraft, and LAB attacks had made shipping operations unsustainable. The Japanese army in China, the Philippines, and the Dutch East Indies began to experience critical supply shortages. Fuel, ammunition, spare parts, food, everything moved by ship, and the ships weren't moving anymore. The war ended in August 1945 before LAB could be deployed on a larger scale. Plans existed to equip 10 additional squadrons with the system. These squadrons were scheduled to receive modified B-29 seconds with upgraded LAB systems, capable of all-weather precision bombing of Japanese home islands. The atomic bombs made those plans irrelevant. The LAB squadrons were deactivated by November 1945. The equipment was classified and stored. The crews dispersed to civilian life. The entire program disappeared into classified archives. For 40 years, almost nobody knew LAB had existed. The official histories of World War II strategic bombing focused on high-altitude daylight operations in Europe. The Norden bombsight received extensive coverage, both positive and critical. LAB didn't appear in any publicly available documents. The crews who flew LAB missions were instructed not to discuss the system and most honored that commitment. The classified designation wasn't lifted until 1984, when researchers preparing official Air Force histories began accessing wartime records. Even then, LAB remained obscure. It didn't fit the standard narrative of American precision bombing. It used radar instead of optics, flew at low altitude instead of high, operated at night instead of day. It was successful, but in a limited tactical role rather than strategic bombing campaigns. Historical attention focused on dramatic raids over Germany and the atomic bombs on Japan. Nobody wrote books about 3 aircraft sinking ships in the South China Sea. But the engineers and scientists who understood what LAB represented paid attention. They understood that LAB had solved a fundamental problem, translating sensor data into weapon delivery with sufficient accuracy to hit specific targets. That problem didn't go away when World War II ended. It became more urgent during the Cold War, when the United States needed the ability to bomb through Soviet air defenses and weather with nuclear weapons. The LAB architecture, sensor to computer to weapon release, became the foundation of every precision bombing system developed in the 1950s, 60s, and 70s. The SC-717 search radar that equipped LAB bombers wasn't remarkable by modern standards. Its resolution was poor, its range limited, its reliability questionable, but it proved that radar could provide targeting data accurate enough for weapon delivery. That proof of concept justified decades of radar development. The APQ-5 bombing computer was a temperamental collection of vacuum tubes and transformers that required constant maintenance, but it proved that electronic computers could solve ballistic equations fast enough for real-time weapon delivery. That proof of concept led directly to digital fire control systems. The modified Norden bombsight, with its electronic scope replacing the optical telescope, was an awkward hybrid that satisfied neither purists nor modernists. But it proved that existing mechanical computers could accept electronic inputs if the interface was designed correctly. That proof of concept informed every avionics integration program afterward. The modern aircraft cockpit, where information from dozens of sensors feeds into integrated displays that pilot, navigator, and weapons officer all access simultaneously, descends directly from that modified Norden in the nose of an SB-24. Technology doesn't develop linearly, it develops through iterative experimentation, where each generation builds on the successes and failures of the previous generation. LAB succeeded not because it was perfect, but because it was good enough to prove the concept. Radar can guide weapons. Computers can calculate trajectories fast enough for combat use. Low altitude reduces certain vulnerabilities, even as it creates others. These lessons informed the next generation of weapons systems, which informed the next generation, which brought us to the present day, where precision-guided munitions can hit targets with single-digit meter accuracy, regardless of weather, darkness, or enemy countermeasures. The B-24 Liberator, the aircraft that carried LAB into combat, was neither loved nor celebrated. Crews preferred the B-17 for its perceived ruggedness. The B-24 was harder to fly, more vulnerable to damage, less stable in formation, but it had longer range and higher payload capacity than the B-17, which made it ideal for Pacific operations. The SB-24 variant, modified for LAB missions, was even less popular. It flew lower than standard B-24 seconds, which meant more exposure to ground fire. It flew at night, which meant navigation errors were unforgiving. It operated independently, which meant no formation support if things went wrong. But the men who flew SB-24 seconds understood something that doctrine writers and strategic planners often missed. Success isn't measured by the elegance of your technology or the sophistication of your tactics. Success is measured by whether you accomplish the mission. The mission was interdicting Japanese shipping. LAB accomplished that mission more effectively than any other system available in 1944. The technology was imperfect. The accuracy was inconsistent. The operational limitations were significant. But ships sank, convoys dispersed, supply lines failed. The mission succeeded. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.